Hey, welcome back to Calculus. In section 3.9, we're going to take a look at how to solve a family of problems that people usually call related rate problems. So you can take a look at our objectives there. I'll let you read them. The main objective really is to sort of get used to what a related rate problem is and how to go about solving it. The main technique is implicit differentiation. All right. So I'm going to introduce the whole idea of related rate problems and what they are just with an example. So let me scroll up so that the example is on the top of your screen there. And let's check it out. So it says that some oil has spilled from a tanker. And this is a classic mathematics problem. We're going to assume that this oil is spreading in a perfect circular pattern, like all oil spills do. So it's spreading out in a perfect circular pattern. And the radius of that circle is increasing at a constant rate of 2 feet per second. All right. I'm going to highlight that phrase because that is a statement about a derivative. The radius is increasing at 2 feet per second. It's a statement about a rate. And then we're asked, how fast is the area of the spill increasing when the radius is 60 feet? Okay, so that's another statement about a rate. How fast, that's a rate keyword, is the increasing, the area is increasing. Those are rate keywords, and we want to know when that's true, what that rate is when the radius is 60 feet. All right, so how do we go about trying to solve a problem like this? Let's draw a little picture. Let's draw a little picture. So I'll draw a circular oil spill here. It doesn't have to be a perfect circle. I think my magic whiteboard here might give me one. There's a perfectly round circle. Maybe I'm visualizing that as the area of this oil spill, and that that circle has a radius. And I'm going to write that radius r of t because it's changing in time. Yeah. So in other words, the two quantities that are changing, I'm going to list them. R of t, the radius of the oil spill. I'm just going to write briefly radius. It's changing, and again of t because it's changing in time. Also the area. The area of the spill is changing in time, so I'm writing it as a of t. All right. And we were given some information about r of t. We were given, I'm going to write it in calculus language, that dr dt is equal to 2. And I'm going to put the units in here. It's 2 feet per second. Yeah, that's what that yellow highlighted phrase is telling us. I'm going to highlight this equation in the same color because that sentence that the radius is increasing at a constant 2 feet per second is precisely the mathematical statement that dr dt, once I've named r of t, the radius, is equal to 2. Yeah, it's a rate of change, 2 feet per second. It's positive 2 because the radius is increasing. Yeah, what do we want? I'd like to know how fast the area is changing. I've called the area A of t, so its rate of change in Leibniz differential notation is dA dt. And in particular, I want to know dA dt when r is equal to 60. Okay, so I'm going to highlight that want dA dt in blue because that is exactly what I colored in blue up in the statement of the problem. How fast is the area increasing? So in calculus language, they're asking me, what is the value of dA dt when r is 60? And we know it's going to be a positive number because this oil spill is getting bigger. So here's kind of the main idea of a related rate problem. We look for, I've done kind of a first main step. I've identified rates that I know, and I've identified the rate that I want to know. Yeah, it was useful to draw a little picture over here to kind of visualize it, and I've named my variables. And now I want to look for a relationship between those quantities that are changing. Yeah, so this is kind of one of the things that makes these sort of a little bit harder problems is that no one will whisper in your ear. You have to think to yourself, well, how is the radius and the area of a circle related? Well, they're related by the equation. The area of a circle, you recall from geometry, is pi times the square of its radius. Yeah, that's an equation that relates the area and the radius of a circle. So then the idea is we differentiate that equation with respect to t. We differentiate implicitly with respect to time. So I'm going to take the derivative of the left-hand side with respect to time, and I'm going to take the derivative of the right-hand side with respect to time. Why am I saying implicit? Well, because r and a both depend on t, but I don't have those functions explicitly. But you'll see as we move through this calculation, we don't need them. Right? We can carry out the right-hand side of this. Pi is a constant. The derivative of r squared is 2r, but since I'm differentiating with respect to t, I have to multiply by dr dt. That's the chain rule. That's the implicit differentiation. And I'm just going to write this dA dt again. And in a distinct highlighting color, I'm going to emphasize that from a relationship between the variables that are changing, differentiating that gives a relationship, an equation, if you prefer, between their rates of change. All right. So differentiating a relationship between quantities that depend on time gives an equation that involves their derivatives. And now in that equation that involves the derivatives, the thing that I want is showing up. Yeah, I won't highlight it again. I'll just underline it. I'd like to know dA dt. It's not going to look very good to underline this in yellow, but I'm given dr dt. I know that. And in particular, I want to know it when r is 60. So we can finish out this calculation by saying, okay, well, let's just substitute in pi is pi, 2 is 2. I'm going to replace r with 60 because we wanted to know this rate when r was equal to 60. And the dr dt I'm going to replace with 2 because we were given the dr dt is 2 feet per second. Yeah. If you want to dimensionally check this equation, let's see what these units are. Pi and 2 are unitless. 60 is a measurement that's in feet, and this 2 was in feet per second. And when you multiply feet by feet per second, you get square feet per second. That's the right unit. That's the right unit on this area. So if we multiply that out, what do we get? 2 times 60 times 2 is 240. So if you like exact answers, there you go, 240 pi square feet per second. I'm just going to write this like this, feet squared per second. Or if you want to get out your calculator, I'm just going to round this to the nearest whole number. That's about 754, I think, square feet per second. Yeah. So I think it's nice to answer the question in a complete sentence. I don't want to belabor this video and make it too long, but the question was, I'm sorry about all the scrolling, how fast is the area of the spill increasing when the radius is 60 feet per second? So my answer is the area is increasing at 754 feet squared per second when r is 60. Yeah, it's a nice way to answer a related rate question is with a complete sentence. I'll be kind of asking you to do that in your homework and on the activities and also on your exams to explicitly answer the question, including appropriate units. It's important. Yeah, 754 doesn't really mean all that much. 754 square feet per second, that's a measurement that I understand. Cool. Okay, so pause the video, think about the details here. I'm going to reveal a little strategy about what we just did. This isn't a recipe to solve all related rate problems, but it's certainly something you can kind of hang your hat on and try as you start to read these things. In general, don't feel bad if you read the problem and don't know how to do it right away. Nobody can read a problem and know how to do it right away. The thing is, you have to keep reading it and understanding it and trying to see if you can sort through these steps. So what did we do up there? Well, I certainly think that it was handy to draw a picture. Yeah. I started by drawing a picture. If nothing else, it helps me kind of understand the relationship between my variables. So I like that first step. Draw a picture. Label, identify and label everything that's changing in the problem. Yeah, but only relevant quantities. Like in our oil spill example up there, the circumference of that circle was also changing in time, but I didn't talk about it because I wasn't given information about it and I wasn't asked about it. So you want to find and label the relevant quantities that are varying. Okay, and then of those quantities, you have to identify which rates of change do you know and which one do you want to find. You have to know all but one of them. In our oil spill example, there were just two quantities, A and R, and we knew dr dt, we asked for dA dt. In general, you have to know all but one of the rates of change. And then step three can be a doozy. It depends on experience, and you might have to do some, looking up some formulas, but you need to find it. Once you've identified the quantities that are varying and what rates you know, then you need to find some relationship between those quantities. In our previous example, that relationship was A equals pi r squared. All right, it'll depend. You'll see I have some other examples down below, but they'll come from geometry, usually, relationships, triangle laws, so on and so on. Once you have that, it's kind of downhill. If you have that relationship between the quantities that are variable, you differentiate it implicitly with respect to time. That's going to give you an equation that involves the rates of change, all but one of which you know. And you solve that equation by plugging in, just like we did. Once we had that differentiated equation, everything we knew we could plug in, and we solved the equation for d a dt. All right? So you evaluate that derivative at the appropriate point. So you can kind of keep these steps in mind as you try to proceed through these related rate problems. Let's just look at another example. Okay, so scroll up here. Second example is involving the context of a game called baseball. If you're not familiar with baseball, it's okay. I'll kind of translate here. So it says that a baseball diamond is a square whose sides are 90 feet long. Okay, so I'm going to draw that square. I'm going to draw it in a somewhat unusual oriented way. Unless you're familiar with the game of baseball, then you're expecting me. And the vertices of this square in a big game of baseball have names. One of the vertices is called home, and then the other ones are enumerated by numbers, 1, 2, and 3. They're called first, second, and third base. And this is a square. These are 90-degree corners, and the side lengths of this square are 90 feet. So that's just taken from the paragraph. It's a square whose sides are 90 feet long, and a player is running from second base to third base at 30 feet per second. So somebody is running from second base to third base. So that's from here this way. And they're running at 30 feet per second, well, when they're exactly 20 feet away from third base. So I'm just going to mark in my picture here. Maybe that's like there. So when this person is 20 feet remaining from third base, they're running at 30 feet per second. And then the question is, what's the player's distance from home changing at that instance? And if it's not clear, let me just emphasize it in the picture. By the distance from home, I mean that distance. All right, so imagine like the straight line distance from this runner to home. Okay, so we're being asked a question about that distance. I'm going to label it. This is kind of identifying the quantities that are varying. I'm going to label that distance. I think I'm going to call it y. Okay, so y, if you want to write it, y of t, it's changing in time. It's the distance from the runner to home. All right, what else is changing? Well, there's the distance from the runner to third base. I'm going to call it x. So it's the distance from the runner to third base. It's labeled in the picture there. It's changing, right? What were we given? What are the statements in this problem about rates, right? So we're saying that this runner, sorry about that, this runner has a speed of 30 feet per second. That's a rate. So when you're reading these things, you're looking for words like that. Increase, decrease, per, right? This word per is always in a rate. So I'm looking for those things. 30 feet per second at the instant that they're 20 feet away. What do we want to know? We want to know how fast the distance is changing, right? So that's another buzzword, changing. How fast is a distance changing? That's a rate. All right, so if I start translating that stuff into calculus language, what were we given? We're given the rate of change of x. We're told how fast that distance is changing, 30 feet per second. But be a little bit careful here. Watch what I write. I'm going to write that dx dt is negative 30 feet per second. So you might be asking yourself, why the negative sign? Well, that's from the context of the problem. It's negative because x is decreasing. Right? As this runner runs towards third base, the distance I've labeled there called x is getting smaller. There's another distance. I'm not going to bring in new variables, but I could have labeled this. This is also changing in the problem. Yeah, and if I did, its derivative, whatever that variable you'd call that red length there, its derivative would be plus 30 feet per second because it's increasing at that rate. But I chose to use the variable x because, well, it gives me a chance to use a triangle law here in a second. And it's also when x is the distance I was given. So we're given that dx dt is minus 30, well, at least when x is 20. Yeah. So they're running at the speed at that instant. What do we want? Well, I want dy dt. I want dy dt when x is 20. So we're kind of, in terms of our steps, we've drawn a figure. We've identified the quantities that are changing. We know the rates we know the rates that we want. So now I'm looking for a relationship between x and y. Yeah, x and y, well, and 90 are the side lengths of a right triangle. So one particular relationship is that x squared plus 90 squared is equal to y squared. Yeah, so we can certainly differentiate that equation with respect to time. And when we do, what are we going to get? We're going to get some dx dt's, we're going to get some dy dt's. Okay, so let's do it. So we differentiate both sides with respect to time. So on the left-hand side, we'd get 2x dx dt, implicit differentiation. Derivative of 90 is 0, 90 squared, excuse me, it's a constant. Derivative of y squared is 2y dy dt. All right. So what do we got to do? We got to solve this for the quantity that I want to know. What's the quantity that I want to know? I want to know dy dt. So dy dt in this equation is right there. So that means I need to be able to plug in everything else. Okay, well, let's just check to see if we know what we're going to plug in. I know what I'm going to plug in for x. I'm going to plug in x equals 20, because that's when we're trying to do this. I know what I'm going to plug in for dx dt. I'm going to plug in minus 30, right? Because that's the rate at which x is decreasing at this moment. The 2's are 2's. What are we going to plug in for y? We have to know what that y value is. Well, there we have to do a little bit of a side problem, because y is the third side of this right triangle. Well, if x is 20, then the Pythagorean theorem will tell us what y is. So we have to do a little bit of side math over here. If x is 20, then we get 20 squared plus 90 squared is y squared. Yeah, or 400 plus 8100 is y squared. So y is the square root. I'm going to take the positive square root because it's a distance of 8500. So that's what I'm going to plug in for that y variable there. So let's do it. Let's do the algebra. If we say divided both sides by 2y, so I'm going to just write this as dy dt, divide both sides by 2y, so we get x over y dx dt. And now we can start plugging in. So we said that x was going to be replaced with 20. Y is going to get replaced with square root of 8500. And dx dt is minus 30. Yeah, and you can get out your calculator and check out that that is, well, it's negative 600 over the square root of 85. I'll put in the units here in a second, so let me write that. Negative 600 over the square root of 8500. And what are the units on that thing? Y is measured in feet, time is in seconds, so that's in feet per second. And if you want to give a decimal approximation, say to the nearest tenth, it's about negative 6.5 feet per second. Okay, and why the minus sign? Well, because that variable y is decreasing as this runner is approaching third base. If you can still see in my picture up here, that this distance from the runner to home is getting smaller. When the runner gets to third base, that distance will be 90. All right, so if I wanted to try to practice my own good advice here about writing a sentence, I should summarize here. I don't want the video to be too long, but let me just remind myself of the question. At what rate is the player's distance from home place changing at this instant? So I'm going to answer when x is 20. The distance from home, I'm being brief just to keep the video short, is changing at minus 6.5 feet per second. Or if you prefer, you could say it's decreasing at 6.5 feet per second. It's the same thing. If you include that it's decreasing, you can erase the minus sign. Okay, I think I'm going to cut this video here. I have 2 more related rate examples I'm going to do, but I'm going to cut this video here so that I'll make 2 short videos instead of 1 super long one. All right, so soak that in, take a break, get something to drink, and then come back and watch part 2.